Now let's see how we use Colab to provide the dynamic programming algorithm to solve this problem. So first, we introduce piecewise function we use. Actually, this is the same function we do our exercise. There are 3 pieces. So the first piece from 0 to 1, the gradient is 100. The second piece from 1 to 2, the gradient is 80. And then the third piece from 2 to 3, the gradient is 50. So similarly, we set a discretization rate. We define the resolution. So that means each time step here is from 0 to 1 is delta t. And then here we set delta t to be 1 divided by the resolution, which is 0.005. This is a relatively fine resolution. If you want to accelerate the algorithm, you can reduce the resolution to a small number. If you want to achieve a better accuracy on the final decisions, you can further increase the resolution, and then the computational time will be increased as well. So similarly, we give the range from 0 to 3, and then based on the resolution, we generate the time axis. So the length of the time axis is given by t. And then similarly, we use our piecewise expression for expression of d, and then we can plot this curve. So first, let's see what we call is our one-step cost. For example, this is t0, this is t1. So we will calculate the shaded area and then evaluate its fixed cost, CF, when we have one shipment, and then we have the inventory waiting cost times this area. Let's see how should we achieve this. Here we define a function to calculate this one-step cost, call it one shipment cost. And then the parameters we give it is the axis, and then this is a cumulative demand function. And then to determine the intervals, we give the index. Here we use the index of t0 and t1 because when we calculate the values, the index is relatively easier to calculate. So for example, if we have t1 equals to 1, and then because the resolution is 200, so the index for t1 actually is 200. Definitely the index for t0 equals to 0, the index will be 0. Okay, so we call this index. We call the index for t0 is I t0, and the index for t1 is I t1. Definitely we give the parameter for CI and CF. Okay, so the calculation for the cost, the one-step cost, is pretty easy. We first calculate the resolution based on the one step on the t-axis, and then the area can be calculated based on a numerical integral, which we just use a very simple integrals. Remember, the shaded area from t0 to t1 is given by dt1 minus dt. Okay, so the shaded area here, we use the index directly. So the index is at t1 is it1, so dt1 is calculated based on d at the index of it1. And then dt, we just use each time step to estimate, and then the delta t is this delta t here. Okay, and then the range is given by t0 to t1, and then we give the index for t0 and t1, range from t0 to t1, corresponding to the upper bound and lower bound. And then we calculate the one-step cost based on one shipment fixed cost CF plus the inventory waiting cost CI times the area. Now let's introduce the mechanism we use for dynamic programming. Actually, this is the most critical part for implement dynamic programming. So remember, when we calculate the dynamic programming, we need to calculate this subproblem for T1. And then the subproblem for T1 is based on all the subproblem greater than T1. Remember, we do the backward recursion, so we calculate the subproblem from Tmax gradually back until T0. Okay, so this is a backward recursion. Okay, so when we calculate T1, we have to know that all the subproblems starting from the values greater than T1. So to make sure that this value is calculated, we do not want to calculate the subproblem for multiple times, because that would be exponential in calculation. So in this way, we try to store all the values from t1 to its larger time index until tmax. So to achieve this, we define a total cost as a dictionary. So if you are not familiar with dictionary, you can just consider it as some data structure which can store the value together with some index. Okay, so definitely we start from define the index of tmax. This is just the total number of indexes in the time axis minus 1. And then we give the first total cost at tmax. Remember, we have introduced that the subproblem for tmax, this is easy because we know that the total cost will be 0 because there's no shipment and then all the demands are satisfied. And then we define its shipping time as tmax. Okay, so to store this value, we just create a key that indicates that when we want to calculate the subproblem tmax, we need to know its value for cost and then the time for shipment. So we store this into this dictionary. Okay, and then let's see how should we achieve the backward recursion. When we first solve the problem for t1, there are two cases. The first case is that we just have only one shipment until tmax. So in this case, our one shipment, this will be ti, and then this will be tmax. So this is a special case where the subproblem is just equivalent to a one-step problem. Okay, and then when t1 is in the middle, then the subproblem of ti can be decomposed into a one-step problem and a subproblem. So in this case, we can calculate the cost based on a summation. The one-step cost, this is actually ti, and then until t1. And then this is the total cost from t1. Okay, so after we calculate the summation of the cost, we update the cost based on the smallest value, right? We want to enumerate all possible t1 and then get the smallest cost. So to achieve this in code, we just calculate all the cost and then remember the smallest cost value. And then definitely we need to make sure we know at which time step, so which t1 give us the minimum total cost. This is very useful. Then every time we enumerate all possible t1, we find the minimum value, and finally we can find the minimum cost, the subproblem solution starting from ti, and then we store this value for a subproblem ti. We store the cost, which is a value we get from the enumeration, and then we store the minimum one. And also we know what is a possible value we need to ship to achieve what is optimum shipment time t1 to achieve this minimum cost. And then you can see if we use a backward recursion and then start from tmax until 0, all this value, for example 599, this is the largest index because we have 200 steps within one time unit. We have total tmax is 3, so the largest index is 599. So this is a tmax. We store this cost is 0, shipping time is 599. And then next, we do the backward recursion. We calculate the subproblem for tmax minus 1 unit. And then we calculate its total cost, which is 189.0125. This is a total cost for the subproblem starting from tmax minus 1. And then the shipment time is 599. So that means to achieve the optimum shipment time, we need to just ship once at the index 598. Similarly, we can see 597, the total cost is a little bit larger, and then the shipment index is still 599, and so on. Okay, now let's see how we finally get the result and then plot it to show. So after we have calculated all this total cost backward recursion results, we know the optimal solution for each subproblem, ti. And then for each subproblem, we know what is the cost, some value, and then the shipment time is T1. So this gives us a chain. For example, if we calculate the subproblem T0, we can directly know that the next shipment time will be T1. And then if we solve subproblem T1, we immediately know the next shipment time is T2, and then we find subproblem T2. We all calculated out already, right? So it can have T3, blah, 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 until a certain subproblem Tn, and then you get the optimum shipment time is Tmax, and then we are done. Then we can get all the shipment time is T0, T1, until Tn. This is our optimum shipment schedule. And then definitely we want to convert this result into the cumulative arrival curve. Cumulative arrival curve can be calculated based on the arrival rate per unit time. Remember, we only dispatch at the optimum dispatching schedule, so we can just calculate the amount of items we ship every time. So for example, if this is T1, then the number of items we ship should be dT2, which is here, minus dT1, which is here. Arrival rate at each shipment time can be calculated by the demand value at the next shipment time minus the cumulative demand value at this shipment time. Here we plus 1 to adjust the numerical error. Okay, and then we calculate the cumulative arrival time and then to plot it in the following curve. So in our previous calculation, we can find out our optimum shipment time should be T0 equals to 0, T1 equals to around 0.65, and then this is around 1.4, and this is around 2.2. So after we have all these values, we can plot the following red curves. Now let's consider the extended problem where we have a certain capacity, so you no longer can ship at any capacity. We will evaluate the run cost. So to implement this, we simply adjust our one-step shipment function with additional parameter capacity. And here we just consider a very simple realization. Definitely this is not the most efficient realization. We just implement this for demonstration purpose. So here we introduce a constraint, implicitly define a constraint with a big number. So that means if you ship something, for example, if you want to ship a load which is greater than Vmax, we just assign a cost for this decision with a very big number. Here we use 999,999 to indicate an infinity number. So in this case, when you solve the problem, you minimize. Remember, every time you solve a subproblem, you calculate a minimization for a possible T1. So in this case, if you consider a load larger than Vmax, larger than the capacity, we will have this one-step cost to be infinity. And then in this case, you will not choose this decision in your optimum schedule. So that's very easy to be realized. If you have a load, which is dt1 minus dt0 here, then we just return an infinity number, which indicates a very high cost. With this adjustment, we can guarantee that the load will be kept by the Vmax. Okay, so after we extend the one-step shipment function, we can define a capacity or the Vmax, which is the capacity value 40 here for demonstration. And then definitely we can consider CR and CI at the same time. We don't need to consider the extreme scenario where either of this value is much larger than the other. In this case, they are both 10. Okay, so when we have this Vmax, we can use our extended one-step shipment cost function with capacity here, okay, and then all the rest are the same. And here we show that this is our previous total cost function for the subproblem. And then in addition, we calculate our run cost. Our run cost is based on CR Vmax and then Tmax. And then we can have our total cost listed here. Okay, and then you can see when we have this bounded 40 as our capacity, so the Vmax is 40, so we can see the optimum dispatch schedule is definitely changed. Now you need to dispatch 1, 2, 3, 4, 5, 6 times. So now you have 6 dispatches Previously, you only have 4 dispatches. So that indicates if you consider the run cost and then the capacity is bounded, you will typically ship more times, balance the run cost.